Well, I'll start out just by save a little time here by saying that this is really a discussion of sample provenance. Okay, so we hope that the South Circumpolar geological map is useful to everybody, and I'll outline a little bit about that as well. But the key here is sample provenance. That is to say, what is the origin of the samples that we're going to get, and where does that go? In terms of how do we determine where to go in relationship to sample provenance? The geological map provides that information because we have topography. We have geological map of the individual craters. We have their ages based on morphology, as well as there we go. Thank you. As well as essentially crater size, frequency distribution, absolute model ages, etc. So this is work by my colleagues at the Vernadsky Institute. So I'll just press on with slide 2. And you can see here that, in fact, this area, of course, is great scientific interest. Concentration of hydrogen in the regolith, potential presence of ground ice, ejected from the South Pole Aitken Basin. I mean, that's like a holy grail, if you will, for chronology and mantle, etc. And it's also a destination for future lander-oriented interplanetary missions. That's why everybody's going there. NASA, JAXA, Roscosmos, ESA, CHENSA, Israel, ISRO, individual companies are going there, okay? So we really need a robust support for these missions, and we did this circumpolar region geological map that Jim Skinner described very early on. Next, please. So what's the story here? Okay, so if we think about this, the highlights are that the SCR lacks extensive Mare regions. So as I said before, this is most similar to Apollo 14, Apollo 16, and the Luna 20 sites. It's dominated by overlapping deposits of impact craters and basins, and this really makes the geological history of individual regions difficult to determine. And it makes the provenance, that is, that fancy word for where did the rocks come from, of return samples potentially really enigmatic. So we need to try to figure out what that sequence is, where the eject is, and how it comes together. Next, please. When we try to do that, that's why we did this geological map, if you will. The map portrays units, features, all the kinds of things you'd want to have in a geological map. It was made with standard geological U.S. Geological Survey and national guidelines, if you will, the North American Code of Stratigraphic Nomenclature. We utilize the mapping, et cetera. Very, very traditional things, of course, adjusted for planetary conditions and data availability, as Eugene Shoemaker, Jack Macaulay, one of my personal heroes, Don Wilhelms, and others pioneered years ago, okay? So we defined several major types of units. Okay, you can see here, and we also did absolute model ages for over 200 of these units, and this quantifies a relatively dated correlation chart. So we have the relative dates based on superposition as well as degradation state, and then we have the absolute model ages based on 200 crater counts. Next, please. So in this map, if you will, we also we didn't just map the South Pole Aitken Basin, we did a statistical study on the South Pole Aitken Basin. We looked at the interior topography, we compared to known oblique impacts, we estimated the ejecta thickness decay based on the asymmetry, and we mapped where we interpreted the SPA ring massifs to be so that we could have those as primary targets as well for the upcoming. And of course, they're all over the place because we're sitting on the rim of the South Pole Aitken Basin. Next slide, please. Another thing, of course, was the geological units. Okay, so we mapped smaller basins, we mapped plains, we mapped craters and degradation states, et cetera, et cetera. And these are put into, of course, the geological units, the DOMU, et cetera. And next, please, we also mapped out the geological structures. There are wrinkle ridges and a few graben here and there, and then their orientations, that's in the paper as well. Next, please, too. Next, please. Sorry. We have a detail, this is standard traditional geological approaches as pioneered by the U.S. Geological Survey, North American Code of Stratigraphic Nomenclature, et cetera. And this is what I'm looking, you look at this here, we obviously, as we are tradition guides us to do, we separated out descriptive units from interpretations. And this is the DOMU that you would, again, put into the mix master because, in fact, when you land there, it's going to be a mixture of all of these things. Next, please. Okay, so we did 200 units and features, and this again adds absolute ages to the relative age chronology. That's in a paper as well. Next, please. We put together a series of geological era sequence of maps, Copernican era, Tassini, Ambrium, and back into time, so you can kind of like study things in that relationship as well. Next, please. And we then, of course, this is the meat here, if you will. For each landing site, we did a previous paper that's in Solar System Research where we looked at the ejecta decay using different models. Caleb Fassett for large basins, Buck Sharpton for smaller craters, and other experimental data to map out the thickness decay and estimate the thickness decay as a function of radial range from individual craters. That's how we added thicknesses to the relative ages and the absolute ages in the stratigraphy. So we were able to produce cross sections, as you can see here, which are not just superposition, but they are an estimate of the thickness decay and the sequence. And then individual impacts come in and readjust that as well. So this is clear. Next Monday, August 21st, sorry, that next was not for, that was for next Monday. Thank you. August 21st, Luna 25 is scheduled to land in the nearby Boguslavsky crater. And we produced these maps for that and for the interpretation of Boguslavsky by the teams. Next, please. And we've also done this for all the Artemis sites, if you will, and we're working on the robotic landing sites as well. And we prepared detailed stratigraphic columns and geological cross sections for each one. And I apologize for the brown here. We're working to make those colors less dark, and that'll come out in the paper, which is finishing, about ready to be submitted to Icarus as we speak. So we have it for these sites. You can see here we've linked them to the sites in the geology. Next, please. And Artemis, we have them for all the Artemis sites. So we hope this will be really important for the geological mapping. The South Circumpolar region map will provide a regional context, and we encourage people to utilize that and go in and then take a look at these stratigraphic columns to test them, not just accept them, but to test them, and also to use them for essentially mission planning, site selection, and also for mission operations and traverse planning, et cetera. Next, please. So the last slide is geological mapping and stratigraphic sequences, okay? These are the keys to sample provenance, and they address major fundamental questions. But all of these things, it's very complex. These polymorphic breccias are not going to be easy to determine in situ, okay? We need to do sophisticated previous pre-mission mapping and map this out into regional pictures, local pictures of what samples might be there, what the relationships are, and how these things will be brought forward so that we can develop a good sampling strategy. So it's important for landing site selection, making design reference mission, for CONOPS planning, specific mission planning, EVA architecture, traverse planning, astronaut training. Okay, astronaut training. I want to just spend 1 minute on this. Okay, of the less than a minute I probably have. So when Apollo 16 landed, the pre-mission mapping was crater terrain, okay? But the plains unit, the Cayley plains, were interpreted by most people, USGS geologists and a lot of us others too, to be volcanic plains. They were thought to be intermediate between the Mare and the highlands. Therefore, they had an intermediate albedo, et cetera. And when John and Charlie got there, John Young and Charlie Duke got there, they stepped out of the lunar module and said, basically, we're not in Kansas anymore, folks. These are not volcanic, they are impact breccias. And the key point here is the mapping was not about an interpretation. It was about mapping units, and therefore they could then say, gee, we're testing hypotheses here. It's not volcanic, it's impact. And they had enough training at all sorts of craters around the planet. Okay, we took them to field trips a lot of different places here so that they could recognize that and know what to do. That's critical. Okay, it's not about a geological map that tells you the interpretation. It's about testing hypotheses. Okay, these are useful in mission operations, sample selection and triaging. Okay, and also obviously in the analysis of return samples as we saw. So remember that Apollo missions are fundamental resources. Apollo 14, 15, 16, and 17, and in particular 16. Please go back and look at that as you do your mapping and planning to see what the most, to me, analogous site to the South Circumpolar region is going to be. Thank you very much, and I hope this is useful.